On this slide, we're reviewing some of the trig entities that we'll use occasionally in this chapter and the next one. These top ones up here, we'll use them every so often, but not all that much. They're just kind of some of the random ones from trig class that you should have seen before. For example, these first two here are showing you how you can change a cosine into a sine, or vice versa. That can be important, as we're going to see later on. It's going to turn out that we're actually going to base everything on cosine in this class for all of our phasor stuff, which I'll explain a little bit later. The next two are what happens if you're adding or subtracting angles inside a sine or a cosine. Again, we won't use those very often, but oh well. This one right here, that's how you convert angles between radians and degrees. Again, it's one of those things that people probably should know from in the past. On the other hand, this last part right here, this is going to be incredibly important in exam 3 material. And this first thing here is called Euler's identity. But before I get more into that, what I want to kind of explain is what we're even trying to do down here. So let's suppose we have the number 3 plus 4j. Now j here, we are using that instead of I like you do in a math class in order to find the square root of -1. It's the imaginary number for us, so keep that in mind. And what we're going to do is we're going to take this number 3 plus 4j and we're going to graph it on this axis here, where my x-axis is going to be the real part and the y-axis the imaginary. So I go 3 to the right and 4 up, and then this point over here, that would be the point 3 plus 4j. So we're taking our imaginary numbers and we're turning them into xy points, and then we're going to go ahead and turn those into polar coordinates. And so for polar coordinates here, you should know from other classes, is you draw this little triangle here. You have the angle theta and the r here. And we can find our r from the square root of x squared plus y squared. That's my formula right down here. And you're going to get 5 for that. And then we can find our angle tangent theta is y over x is 4 over 3. And when we find our theta, we get 53.1 degrees. Now I am going to be more commonly using degrees, even though radians is maybe preferred, but most people are more familiar with degrees. Now here's how we're going to write our polar format. We're not going to write it as an ordered pair like you used in like Calc 2 or something. We are going to write it in the following way. 5, the radius, then we're going to write the angle sign, and then 53.1. And this is going to be called phasor notation. And that's how we're going to deal with our complex numbers. We're going to turn them into phasors. Now, what if I had something like the following? What if I had -5 plus 12j? Let's go ahead and convert that into phasors here. So I'd go -5 and up to 12, and I get my number over here. Now the reason why I'm doing this example is I can find my r, the same formula. And we're going to get 13 here. And then I do my tangent theta is y over x, 12 over -5. However, if I were to just do tangent inverse, that would give me the wrong answer, because tangent inverse only lives on the right side of the x-axis, right, from angles from -90 degrees to +90 degrees. And so if you're in quadrants 3 or 4, when you do tangent inverse, you have to add 180 degrees to it to get the right answer. So I'm giving this example here to make sure to remind you about that. Now, if I go ahead and look at my calculator now, I'm going to get theta of 112.6 degrees. And so in phasor notation, this would be 13 angle 112.6. And it's going to be important for us to go back and forth between phasors and regular wave writing, also called rectangular. And that's from these last two formulas here. So you would say, okay, 13 cosine of 112.6 plus 13 sine 112.6 j, and that should give you negative 5 plus 12j.